The difference between calculated conductor fill and Annex C of the National Electrical Code arises primarily from the shape of the conductors themselves, specifically when dealing with thermoplastic high heat resistant, or THW, conductors. Annex C provides simplified fill tables, particularly geared towards residential branch circuits. These tables are designed for quick reference using common conductor sizes and conduit types. However, a critical assumption underlies these tables that all conductors are perfectly round. This assumption holds true for many conductors, but not for all, including THW conductors. THW conductors often exhibit an oval shape, rather than a perfectly circular one. This seemingly minor detail significantly impacts the available cross-sectional area within a conduit. Because of their oval form, THW conductors occupy less area than a round conductor of the same American wire gauge or AUG rating. This difference in shape leads to discrepancies when calculating conductor fill mathematically versus relying solely on Annex C tables. When performing conductor fill calculations, it's imperative to account for the actual cross-sectional area of the conductors being used. For THW conductors, this means using the area that reflects their oval shape, rather than assuming a round profile. This adjustment will invariably result in a lower allowable number of conductors compared to what Annex C might suggest, since the Annex assumes round conductors. Consider the example of number 14 THW conductors. The oval cross-sectional area is 0.139 square inches. Now let's consider 1-inch Schedule 80 polyvinyl chloride, or PVC, conduit which has a 40% fill capacity of 0.275 square inches. Dividing the conduit's available area by the conductor's area, we get 0.275 divided by 0.139, which equals approximately 19.8. This suggests that you could theoretically fit 19 number 14 THW conductors into this conduit. However, Annex C might show a different value, due to the round conductor assumption. It's important to remember the role of Annex C within the National Electrical Code. The preface to Annex C explicitly states that it is not a mandatory part of the code. This means that it's not strictly enforceable, but rather serves as a guideline, particularly for residential applications. Therefore, findings based on Annex C might be deemed acceptable for residential installations where a simplified approach is desired. However, for non-residential applications, or situations requiring greater accuracy, relying solely on Annex C may not be sufficient. In these cases, performing mathematical calculations becomes essential. This involves using the actual cross-sectional area of the conductors to determine the allowable number of conductors within a given conduit. Firstly, determine the conductor type such as THHN, THW, or XHHW, and its corresponding cross-sectional area from Chapter 9, Table 5 of the National Electrical Code. This table provides the dimensions and areas of various conductor types. Secondly, identify the conduit type being used, such as electrical metallic tubing, or IMT Schedule 40 PVC, or rigid metal conduit, or RMC, and determine its inside area from Chapter 9, Table 4. This table lists the dimensions and areas of different conduit types. Thirdly, determine the allowable fill percentage for the conduit. Table 1 of Chapter 9 specifies the allowable fill percentages based on the number of conductors in the conduit. For example, for 1 or 2 conductors, the allowable fill is 40%, and for 3 or more conductors, the allowable fill is 40%. Fourthly, calculate the allowable fill area by multiplying the conduit's inside area by the allowable fill percentage. For instance, if a 1-inch EMT has an inside area of 0.864 square inches, and the allowable fill is 40%, then the allowable fill area is 0.864 multiplied by 0.40, which equals 0.346 square inches. Fifthly, divide the allowable fill area by the cross-sectional area of a single conductor to determine the maximum number of conductors permitted in the conduit. For example, if the allowable fill area is 0.346 square inches and the cross-sectional area of a number 12 American wire gauge, or THWN conductors 0.133 square inches, then the maximum number of conductors permitted is 0.346 divided by 0.133, which equals approximately 25 conductors. When performing these calculations, ensure that all measurements are in the same units, typically square inches. Refer to the appropriate tables in Chapter 9 of the National Electrical Code for conductor dimensions and conduit sizes. Always round down to the nearest whole number when determining the maximum number of conductors, as you cannot have a fraction of a conductor. In summary, the discrepancy between mathematical calculations and Annex C for THW conductors stems from the difference in cross-sectional area between oval and round conductors. For accurate results, particularly in non-residential settings, it is best practice to perform mathematical calculations based on the actual cross-sectional area of the conductors being used, rather than relying solely on the simplified tables in Annex C. Always consult the latest edition of the National Electrical Code for the most up-to-date information and requirements. When dealing with electrical installations, safety is paramount. Always to energize circuits before working on them, and follow all applicable safety procedures and regulations. If you are not qualified to perform electrical work, consult a licensed electrician. The National Electrical Code, or NEC, provides guidelines for safe electrical installations. While Annex C offers simplified tables for conductor fill in residential branch circuits, these tables are based on the assumption of round conductors. However, THW conductors are often oval, having a smaller cross-sectional area than a round conductor of the same American wire gauge or AUG rating. When calculating conductor fill mathematically, the oval cross-sectional area of THW conductor should be considered. This will result in a lower allowable number of conductors compared to the tables in Annex C, which assume round conductors. Annex C is not part of the NEC, as stated in its preface, and is not enforceable. It can be used as a general guideline for residential applications. For non-residential applications or for greater accuracy, mathematical calculations should be performed to determine the allowable number of conductors based on their actual cross-sectional area. The discrepancy between mathematical calculations and Annex C for THW conductors is due to the difference in cross-sectional area between oval and round conductors. For accurate results, it is recommended to perform mathematical calculations based on the actual cross-sectional area of the conductors. Always refer to the latest edition of the NEC and consult with a qualified electrician for specific applications. For example, consider a scenario where you need to determine the maximum number of number 12 American wire gauge, or AUG, THWN conductors that can be installed in a 3/4-inch electrical metallic tubing, or IMT conduit. Firstly, you would refer to Chapter 9, Table 5 of the NEC to find the cross-sectional area of a number 12 AWG THWN conductor, which is 0.133 square inches. Secondly, you would refer to Chapter 9, Table 4 of the NEC to find the inside area of a 3/4-inch EMT conduit, which is 0.533 square inches. Thirdly, you would refer to Chapter 9, Table 1 of the NEC to determine the allowable fill percentage for more than 2 conductors, which is 40%. Fourthly, you would calculate the allowable fill area by multiplying the conduit's inside area by the allowable fill percentage. 0.533 multiplied by 0.40 equals 0.2132 square inches. Fifthly, you would divide the allowable fill area by the cross-sectional area of a single conductor to determine the maximum number of conductors permitted. 0.2132 divided by 0.133 equals approximately 16 conductors. Therefore, you can install a maximum of 16 number 12 AWG THWN conductors in a 3/4-inch EMT conduit. In contrast, if you were using number 12 AWG THW conductors, which have a slightly larger cross-sectional area, the maximum number of conductors permitted would be slightly lower. Always ensure that you are using the correct cross-sectional area for the specific conductor type being used. Another important factor to consider is dirting. When multiple current-carrying conductors are installed in a conduit, the ampacity of each conductor must be derated to account for the increased heat generated by the conductors. The derating factors are specified in NEC Table 310.15. B3. For example, if you have more than 3 current-carrying conductors in a conduit, the ampacity of each conductor must be derated by 80%. This means that if a number 12 AWGTHHN conductor has an ampacity of 30 amps, its ampacity must be reduced to 24 amps when more than 3 current-carrying conductors are installed in a conduit. It is crucial to consider derating when determining the allowable number of conductors in a conduit to ensure that the conductors are not overloaded. Overloading conductors can lead to overheating, insulation damage, and potentially fire hazards. Always consult the NEC and follow the recommended derating procedures to ensure safe electrical installations. In addition to conductor fill and derating, other factors to consider when installing conductors in a conduit include bending radius, support requirements, and proper termination techniques. The NEC specifies the minimum bending radius for different conduit types to prevent damage to the conductors during installation. The NEC also specifies the support requirements for conduits to ensure that they are properly secured and do not sag or become damaged. Proper termination techniques are essential to ensure a reliable electrical connection and prevent loose connections, which can lead to overheating and fire hazards. Always follow the manufacturer's instructions and use approved connectors and termination methods. Furthermore, it is important to consider the environmental conditions in which the conduit is installed. For example, if the conduit is exposed to direct sunlight, the conductors may need to be derated further to account for the increased ambient temperature. If the conduit is installed in a wet location, the conductors must be rated for wet locations. Always select conductors and conduit types that are suitable for the specific environmental conditions in which they will be installed. In conclusion, determining the allowable number of conductors in a conduit requires careful consideration of several factors, including conductor fill, derating, bending radius, support requirements, termination techniques, and environmental conditions. Always consult the latest edition of the NEC and follow the recommended guidelines and procedures to ensure safe and compliant electrical installations. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are not comfortable performing the work yourself. A licensed electrician has the knowledge, skills, and experience to ensure that electrical installations are performed safely and correctly. By following the NEC and consulting with qualified professionals, you can help to prevent electrical hazards and ensure the safety of people and property. Furthermore, understanding the nuances between calculated conductor fill and the simplified tables in Annex C of the National Electrical Code, particularly concerning THW conductors, is paramount for ensuring electrical safety and compliance. While Annex C offers a convenient reference for residential applications, it's crucial to recognize its limitations, especially when dealing with non-round conductors like THW. The oval shape of THW conductors necessitates a more precise calculation of conductor fill to avoid overcrowding and potential hazards. Relying solely on Annex C in such cases can lead to underestimation of the actual space occupied by the conductors, potentially resulting in overheating, insulation damage, and even electrical fires. Therefore, for critical applications and non-residential installations, prioritizing mathematical calculations that account for the specific shape and dimensions of the conductors is essential. This approach ensures a more accurate assessment of conductor fill, promoting safer and more reliable electrical systems. Moreover, understanding the derating factors outlined in the NEC is equally important when determining the allowable number of conductors in a conduit. Derating accounts for the heat generated by multiple current-carrying conductors in close proximity, which can reduce their ampacity. Failing to apply the appropriate derating factors can lead to overloading of the conductors, potentially causing overheating and insulation breakdown. Therefore, it's crucial to consult NEC Table 310.15. B3. And apply the necessary derating factors based on the number of conductors and the ambient temperature. In addition to conductor fill and derating, other factors such as bending radius, support requirements, and termination techniques play a vital role in ensuring safe and compliant electrical installations. Adhering to the minimum bending radius specified in the NEC prevents damage to the conductors during installation, while proper support ensures that the conduit is securely mounted and protected from physical stress. Furthermore, using approved connectors and termination methods is essential for establishing reliable electrical connections and preventing loose connections, which can lead to overheating and fire hazards. By paying attention to these details and following the guidelines outlined in NEC, you can help to minimize the risk of electrical accidents and ensure the long-term safety and reliability of electrical systems. In conclusion, while Annex C of the NEC provides a convenient reference for conductor fill in residential applications, it's essential to recognize its limitations and prioritize mathematical calculations when dealing with non-round conductors like THW. Additionally, understanding and applying the appropriate directing factors, bending radius, support requirements, and termination techniques are crucial for ensuring safe and compliant electrical installations. By adhering to the NEC and consulting with qualified professionals, you can help to prevent electrical hazards and ensure the safety of people and property.